Okay, so guys, this is the Chapter 7 Study Guide review. I will go through this rather quickly and hopefully it helps you in your exam. Okay, the elements in Group 7A are known as halogens. Okay, you just need to know some of the groups, and that's one of the groups you need to know. I may go to my trusted periodic table. Let me see, that's not my trusted periodic table, is it? This is my trusted periodic table. Okay, so this of course is 1A, 2A, 3, 4, 5, 6, and that's 7A. These are my halogens. So you need to be familiar with fluorine, chlorine, bromine, and iodine. Those are the main halogens that we deal with. This radioactive stuff we don't really need to concern ourselves with now, do we? Okay, so yeah, halogens. Now, elements in group 2A are known as alkaline earth metals. And again, I'll go to my trusted periodic table. These are alkaline earth metals. Beryllium, magnesium, calcium, strontium, barium, and radium. Okay, these are, you don't have to be so concerned with radium though. But yeah, these are my alkaline earth metals in that second group. And let's see. Alkali metals are found in group 1A. Go back. So alkali metals, lithium, sodium, potassium, rubidium, cesium, and of course francium if you want to be concerned with that. All right, which one of these elements is a transition metal? So of course strontium isn't. It's an alkaline earth. Lead is main group. Arsenic is also main group, and of course iron is a transition metal. So going back, so any of these in this block right here, this block of metals right here, starting at scandium on one end, zinc on the other end, and going all the way down to Copernicum. Okay, so yeah, and yeah, and I'm pretty sure actinium is not F block. So yeah, it would be considered a transition metal too. So all of these are transition metals. Okay, so iron of course is amongst that. So yeah, it's right there, atomic number 26. So let's see. A general electron configuration for atoms of all elements in group 5A. Now, of course, if you go to 5A, that's going to be the group with nitrogen right here. Now, notice we can, each block corresponds to an electron. So this is 2s1, and then that beryllium block would be 2s2. Boron would be 2p1, 2p2 would be carbon, and 2p3 would be nitrogen. So all of these would be something S2 and then something P3. So two S's and three P's. So I'm going to go ahead and find out what that corresponds to. So NS2, NP3 would correspond to D, wouldn't it? So the answer there would be D. All right. 6, an element with a general electron configuration for its outermost electrons of NS2, NP1. Okay, that of course is going to be the group with boron in it, right? So boron, aluminum, gallium, indium, thallium. So let's see what we got here. That's going to be group 3A, right? Number 7, how many valence electrons does carbon have? Now guys, remember how you do this. All you got to do is start from the end, whatever that row you're dealing with. Start on the end and just start counting. 1, 2, 3, 4. So carbon has 4 valence electrons. All right. Number 8, how many valence electrons does tin have? So again, you find 10. It's right there. Now remember, once the D's are full, they're no longer considered valence electrons, and that's of course true for the F2. So I'm not going to count these 10 right here. So I just start right here, 1, 2, then I skip all the way to indium, 3, 4. So tin has 4 valence electrons, the same as carbon. It's in the same group, so of course you'd expect it to have the same number of valence electrons. 4, so the answer there is going to be B. Okay. And what is the charge of a monoatomic ion of calcium forms in its compound? So of course you look at calcium. So of course calcium wants to lose 2 electrons. So 1, 2 electrons. When it loses 2 electrons, it's going to have a noble gas configuration. It's going to have the same electron configuration as argon. So of course the answer is +2, which is A, number 10. which of these species makes an isoelectronic pair? All right, now let's see what we have here. Going back to the periodic table. All right, so notice we have, well, when they say isoelectronic pair, they mean have the same electronic configuration. So chloride anion, so chlorine was right there, 17. If you give it one electron, it's going to have the same electron configuration as argon. All right. Now oxygen, if you give it 2 electrons, it's going to have the same electron configuration as neon. So since neon and argon aren't the same electron configuration, that's not a pair. Well, actually, I guess they're looking. We have to look at what they tell us to look at, right? So A, calcium and iron, calcium 2 plus and iron 3 plus. That's of course not the case. O2 minus in fluorine. That's not the case. If oxygen picks up 2 electrons, it has the same electron configuration as neon, and fluorine neutral has the same electron configuration as fluorine neutral. So of course that's not the case. Fluorine and chloride, of course, they couldn't possibly have the same electron configuration. What about chlorine and calcium 2 plus? So if chlorine with a -1 charge. Chlorine with a -1 charge has the same electron configuration as argon. Calcium with a +2 charge has the same electron configuration as argon 2. So the answer, of course, there is D. All right, number 11. Which of these choices is the electron configuration of the aluminum ion? Now, if you guys look at your periodic table, notice that aluminum is right here at number 13. Now, if it has 13 electrons when it's neutral, when it loses 3 electrons, because they asked us the electron configuration of aluminum 3 plus, it's going to have the same electron configuration as neon. So, of course, that's going to be 2s2, 2p6. So let's go ahead and find that, which is fairly stable. Okay. Well, they didn't really have to include the 1s's, but they did. So you find the 1s2, 2s2, 2p6. So the answer is D, of course. Now, we didn't go over atomic radii in class, but I'm going to go ahead and do this. I think you guys can get this. Okay. Now I'm going to. They asked which of these atoms has the smallest radius. So what you do is you just go through one by one, and you eliminate them as you go along. So, if, for example, first I'm going to compare aluminum to phosphorus. Aluminum to phosphorus. Now, before I started studying chemistry, I used to think that, hey, the higher the atomic number, the bigger the atom. Period. That's what I used to think. That's not the case. Now, as we do know, going down a group, the size of the atom does increase. So lithium is not going to be as large as sodium, and sodium is not going to be as large as potassium. And of course, rubidium is going to be bigger than potassium, and cesium is going to be bigger than rubidium. You get the idea. So going down the group, they do increase. But going from left to right, they decrease. Okay, so if I compared aluminum to phosphorus, since they're in the same row, I know that phosphorus is going to be smaller than aluminum. Okay, aluminum is bigger between the two. All right, so now I want to, since they want to know which one has the smallest radius, now I get to compare phosphorus to arsenic. Now, of course, since arsenic is in the same group as phosphorus, they're both pnictogens. Okay, that's the name of that group, by the way. Arsenic is lower, so arsenic would be bigger, so phosphorus, of course, would be smaller. Since they're asking for which one's smaller, I'm still going to go with phosphorus. Then phosphorus and tellurium. Okay, now you're saying to yourself, well, hey, tellurium's over here. Am I comparing apples to oranges if I'm comparing phosphorus to tellurium? No, because even though tellurium is over to the left more, to the right more, it's much further down than phosphorus, so tellurium is going to be bigger than phosphorus. So phosphorus is still the smallest, and I compare phosphorus and sodium. So phosphorus is right here, and sodium is right there. They're in the same row, and of course, they get smaller as you go from left to right in the row, so phosphorus is going to be the smallest. So the answer is B, phosphorus. Okay, 13, they ask which ion have the largest radius. Now the way we do this is it's best to compare uh, uh, if we were talking about ions, the ones that have the same electron configuration, so isoelectronic ions, or you can compare ions in a group. Okay, for example, I could compare all of my alkali metal cations because you'd still get the same trend. As you go down the group, they all have a +1 charge, and as I go down the group, they're going to get larger. So a cesium +1 would be bigger than a lithium +1. But for example, but most of the time you're going to compare things that are isoelectronic, so they have the same electron configuration. So the way this works is if they have the same electron configuration, if they're isoelectronic, the greater the negative charge, then the larger the radius. The greater the positive charge, the smaller the radius, if they're isoelectronic. Okay, so let's see if these are isoelectronic. First, let's look at the chloride anion and the potassium cation. The chloride anion is isoelectronic with argon, and the potassium cation is also isoelectronic with argon. Okay, so since they are both isoelectronic, you compare the one with the largest amount of negative charge is going to be bigger. So chloride would be larger than the potassium. Chloride anion would be larger than the potassium cation. Okay, so chloride. Okay, then I'm going to look at compare chloride to sulfide 2 minus. Okay, so you say, well, hey, you know what? Sulfide 2 minus has an argon configuration 2, electron configuration 2, but it has a -2 charge compared to the -1 of chlorine. So the sulfide is going to be larger. Okay, then I compare sulfide to sodium. So sulfide, all right, sodium +1. All right, I know you're saying, well, they're not isoelectronic with one another, but you know what? Sulfide is isoelectronic with argon, and sodium is isoelectronic with neon. So even though they are not isoelectronic to one another, I know sulfur has a larger negative charge, and in argon is bigger than neon anyway, so I would expect sulfide to still be bigger than the sodium +1 cation. All right, then of course sulfide and oxide, and again, now that's when we get to compare the two in a group. Sulfide and oxide, they're in the same group, so of course sulfide is going to be bigger. So the answer there is going to be sulfide. Okay, so the answer that would be C. And then of course